Well, that's kicking in. Okay. So you guys are probably smarter than me at finding the live stream. So if somebody wants to have a record of that, I tried to send a link to the YouTube channel. Um, and we're going to start by looking at problem 24.6. So let me bring that up here. Let me get that. Let me do a share screen. Just so you know, my intention is to do as little Zoom as possible. But I needed to test a few things. I was telling some folks about this as class was getting started. In particular, I really needed to test the afternoon class, and I'm trying to be fair to everybody and subject everyone to the same amount of Zoom. So I haven't used that other classroom before and the cameras, and so I have a feeling those could end up being some really good Zoom lectures. Well, as far as Zoom lectures go. So I really feel I need to try that. And so that's what I'm doing later today. And all right, enough said about that. Let's just get to it. And all right, so hopefully you can see on my screen, we've got 4 charges arranged at the corners of a square. What is the electric potential or voltage V? We're looking at part A here. What is V at the center of the square? What do you think? Anybody? You can unmute or you can drop it in the chat. I can bring the chat up here. Where is the chat? I'm missing it. There it is. So this is just to kind of remind us last time. You might not remember the formulas, and so this was hopefully to motivate us. Does anybody remember the formula for electric potential for a single point charge? Okay, it's related to that, Jose, actually. It was actually, it was more like U over Q, which if you remember, delta U equals negative work. So it's very similar to what you had said. I don't like to use work in that definition because remember, work relates to a change in potential energy. And so we've got to be very careful, if I could. So this is a good reminder. There's going to be symbols here. We're going to have U, we're going to have V, we're going to have delta U and delta V. And so we've got to be careful with all those things. And it turns out this one happens to equals minus work. So, all right. So that's a good start. All right. What about the exact formula for a point charge? Oh, and if you wanted, if it helps, U is equal to Q times voltage. So that's another formula. And I think that's where he was going. Yeah. Does anybody remember the formula for the voltage? Yeah, KQ over R. Okay, so I'm going to have that on my screen. All right. There we go. All right. And so now let's look again at this problem here. What is V at the center of the arrangement? What do you think?
Would it be 0?
Yeah, it's 0 because if I'm sitting, let me get my annotation back up here. If I'm sitting right here, I have the same distance from all of these, right? I'd have to think carefully. I think it's A over root 2 or something like that. Well, maybe we should figure this out really quick. So this side would be A over 2. This side would also be A over 2. And so this side would be root 2 times A over 2, which is what I think A over root 2, but whatever. They're all the same distance away. So remember the voltage equation, and this is what I was trying to emphasize to get us started again. This is not a vector. That's distance. And so Q could be positive or negative. So if you have a negative Q and a positive Q, the same distance away, those two terms cancel out as far as voltage goes. All right, so let's clear off those annotations and try the next one. So now what about the electric field at the center? So let's say we're trying to figure out the electric field at the center. Is that going to be 0? What's your gut tell you? Oh, there's a chat. Okay, yeah, so I think that's all right. So Jose, sorry, my chat box was covered up there. All right, so and take a look, right? This one is going to pull this way, This one's going to pull that way. They cancel out. This charge right here is going to push that way, and the bottom left charge is going to push that way. So, yep, they all cancel out. All right, so in this case, we see that the voltage and the electric field are 0 at the center. What's going to happen? Will that still be true if the bottom 2 charges are switched? So if we switch the bottom 2 charges, what should happen? So again, we're looking here. If this becomes a negative Q and this becomes a positive Q, is the voltage still equal to 0?
Let's say yes.
Yes. Is the electric field still equal to 0?
No.
No. And so I just wanted to point out, this is something that's a little bit tricky, right? We would see, actually, there's going to be 2 fields pushing this way and 2 pushing that way. So the net electric field would be 1, 2, 3, 4 X components this way. It'd be huge, right? So this would be the electric field if we switch the 2 bottom charges, right? Now, the moral of the story is this: just because voltage is 0 does not mean electric field is 0. I like to think about this in terms of throwing a ball up in the air, right? When you throw a ball up in the air, velocity in the y direction is equal to 0 at max height, but the acceleration in the y direction is not equal to 0 at max height. And so similarly, if you recall, the electric field was equal to opposite the derivative of, now here I'm using the directional derivative called the gradient, the voltage, right? Similarly, we know that A sub y is equal to the derivative of V sub y dt, right? So in these cases, I just want to point out, just because one thing is equal to 0 doesn't mean the other is, right? Even though they're related by a derivative, it's possible that you could have 0 electric field and non-zero voltage, or vice versa. Similarly, we might have 0 velocity but have non-zero acceleration or something like that. All right. All right. I think that's pretty good as a warm-up. So remember, what did we get out of all this? V is K Q over R. It's not the same thing as the electric field. And remember that this thing down here is a distance. All right. Could be positive or negative, right? We don't know. It depends on the sign of the charge. All right. So that's our warm-up problem. Any questions about that before we move on?
And so the potential energy in the middle will be 0 as well?
Potential energy in the middle does not make sense as a sentence, and it's subtle. What I think you meant is the potential energy associated with this charge configuration. And that's a subtle difference. The potential energy is not located anywhere.
Mm-hmm.
The potential energy is stored effectively in the electric fields, which are throughout all of space. So what we typically, did that make sense, the subtle distinction there?
Yeah, I'm trying to wrap my head around it.
Oh, yeah. So let me put it to you this way. Let's stop the screen share for a second, because this is going to relate to what we're doing in just a minute. And let me go to speaker view. Hold on. And let me get me up there. There we go. All right. So let's take a look here. Oh, I'm in the garage now. Whoa. Oh, shoot. Something's stuck. Trying out my new system here. Oh, different lighting. Hopefully this will be a little better. I don't know. We'll see. All right. Oh, smashing stuff back here. All right. All right. So let's start with the Earth and a box. All right. So imagine we have this Earth and the box, right? And obviously it's too big to draw the entire Earth. Normally, back in Physics 161, we used to say, oh, this box has energy mgh. And that's how we started. And we said that because we know when you let go of these things, the box is going to move a lot. And the Earth, even though it does move upwards towards the box, it moves less than a billionth of a nucleus radius or something, right? So technically, when you let go of these, they actually come together. But the Earth is so massive, it has such a small acceleration, we only notice the box moving. Now, in this chapter, we said there was energy stored in there, GMM over R, and I think there was a minus sign in there, right? So this was and maybe I'll pop that into red here really quick, right? So this was the gravitational potential energy stored between the Earth box system. And the reason I say it's stored between the system is because technically, when you release it from rest, both of them start moving. So far, so good, Esteban?
Yes.
All right. So now the idea is, what if we go to, I'm just going to keep it simple. Let's say we have a proton whose mass, and then let's say we also have an electron. All right. Electron. So we have a hydrogen atom, right? Simple system. If it helps, the mass of the proton is approximately 2,000 times, I think it's more like 1,800, the mass of the electron. All right. Now, in this case, we would expect it's a similar situation where the proton is going to have much smaller accelerations, right? They have the same force by Newton's third law, right? These are exerting a Coulomb force on each other. There's a force due to the electric field here, and it's the same size on each of them, right? So we have the same size Coulomb force on each of these two objects. However, because this one is 2,000 times more massive, it's going to have smaller accelerations, but it is still going to move a little bit. Again, the idea is we don't say you have potential energy here, there, or anywhere. It's the potential energy stored in the fields around these two objects, or it's basically these two objects share that potential energy. So it doesn't make sense to locate it here or there. Is that enough?
Yeah, I guess I was thinking like if you put a charge right in the middle of there.
If you put a charge right in the middle of here, let's say this is Q. Sorry, that's a little small, but let's say we put another charge right there. Then all three of them would share the energy because they would all three have motion related to it when you release them, right? And so if you put another one up here, a 2Q, or another one over here, a minus 6Q, the idea is these two would have some potential energy. These two, every possible pair would contribute to the total. And what's tricky is you can't really split it up and just say, well, this is the potential energy that these two share only. Not really. This one has potential energy with this, and every other one with it. This one has potential energy with every other one with it. And so when they all move, as they move a little bit, all of the potential energy terms will change. And that's why we can't just say it's just these two or those two in general.
Okay,
Got it?
I got it.
And we're going to actually look at a problem like that, probably our second problem today. And hopefully that will dial in this issue. All right, cool. So now let's take a look at 24.2 really quick, okay? And I'll get a screen share going. So let's look at 24.2, all right? So we've got some point charges near Nipomo and Lompoc. Yeah, boy. All right. Where did I put my markers? Oh my gosh, they were just in my hand. Here they are. All right. Okay. So quickly, what is the electric potential in Nipomo for these two charges? What's the answer?
Is it 0?
It's 0, right? If you're sitting, oh, whoops, there was a chat there. Oh, sorry, Michael. You're right. I didn't. So sometimes I don't see the chat. I'm going to bring it up bigger on this window over here so I can see it. Sorry about that. All right. Yeah. So if we're sitting up here, isn't it the same distance? And so if you have the same distance, opposite charges, This is 0. On test day, if you just wrote 0 and didn't say anything, full credit for that type of problem. There's sometimes I'll throw you an easy one like that on a test where I'm just like, hey, you're equidistant from two opposite charges. Electric potential is 0. Is the electric field 0 in the POMO?
No.
Which way is the electric field pointing in the POMO?
To the left?
Yeah, because there's going to be a plus charge here, a minus charge there, and that's going to contribute to go that way. All right, so far so good. All right, so now let's say we want to get the electric potential down in Lompoc. All right, so in this case, I'm going to go to the whiteboard and sketch it out. You guys can sketch it on your paper. This is 24.2b. All right, got a minus charge here, got a plus charge here. And then I think there's a coordinate system here. And we're over here in Lompoc. And we're told that distance is A, and that distance is X, I think. All right. Okay. So hopefully, I'm realizing something already about my system here. I gotta move this table a little bit. All right. So in this case, oops, you kinks to work out in the new system here. All right. That's why I'm doing this. Okay. In this case, I'm probably going to write down the V at Lompoc is equal to V plus V minus, meaning the voltage caused by the plus charge and the voltage caused by the minus charge. So we're going to need some distances in here. So that's going to be K plus Q over radius plus K minus Q all over radius for the minus. So you'll see me kind of do this in the workbook sometimes in the solutions. What I'll do is if I have a plus charge and a minus charge, instead of calling them 1 and 2, sometimes I'll say plus and minus as the subscripts. All right. Now, in this case, I hope you agree we could factor out some stuff here. We're going to get KQ times 1 over radius plus 1 over radius minus. All right. So the whole problem boils down. Oh, wait. Isn't
No,
it minus?
minus
Yeah.
1 over.
Yep. Minus that one. Okay, cool. Good catch.
I have a question
Yeah.
about Zoom real quick.
Yeah.
So right now your window is like maybe like 1 inch by 2 inches on my screen. Is there any way for me to zoom in?
Yes. So if you go to the upper right corner, you should see a view button. And there should be a speaker view.
Okay, thank you.
Yep. Also, yeah, good question. Any Zoom questions, interrupt anytime. Also, I'm live streaming this to YouTube. And so afterwards, if you did miss anything from the beginning, we can go back and get that. Okay. Yeah. Cool. Thanks. Other questions? Right on. Okay. So let's go up here. The problem boils down to, right. We see it's very standard physics problem. You just add up the two pieces and get the total. But now here comes the part we got to think. What's R plus in this case? Well, R plus would be that, right? R plus is from the plus charge to the point of interest, whereas this would be R minus from the minus charge. So what would R plus equal in this case?
X minus A over 2.
Sure-ish. I'll say sure-ish. Now, as far as this picture goes, that is a correct answer. And I didn't discover this until I did part C or D when I wrote this up. What if Lompoc happened to be inside of here? Or said another way, what if X was less than? Technically speaking, if X was a small number, less than A over 2, do you agree this wouldn't be a distance? Because it'd be negative. So if you were wanting to be extra careful and make sure this was a positive number, you could stick absolute values on there. Did that make sense, what I'm talking about, or not? Hopefully, yeah.
Yeah, that
Whatever.
makes sense.
Yeah, so you are correct for this problem. In general, if we want to make sure something is at a distance, you could always slap absolute values on, like if you had to make a code. Enough said. All right, how about over here? R minus is going to be X plus A over 2. And again, if we wanted to make sure this was going to work out, we should slap on some absolute values on that. Okay. Now, because if we put these absolute values on there, this is not only valid for Lompoc, it's valid for any X on the X axis. So that's the advantage of the absolute values. All right. Now, from there, I think you agree you could plug in some stuff and get an answer. I want to point out a couple of things, and I'm going to go to the solutions here to speed things up. All right. All right. So in the solutions, right, here's where we get this stuff. I ended up with this result when I plugged that in, and maybe I'll make this even a little bigger. All right. So hopefully you get this result right here. This V total equals something like that. And that looks pretty good. And then I wanted to mention something very briefly about when you see similar denominators, but you have a subtraction here like this. So these are pretty similar denominators. You could do one of two things. You could either do a binomial expansion and just see what that works out to. Or in this case, I chose to do a common denominator. Check this out. If I do the common denominator, I get this cool result right here. And I think you'll agree that probably looks better, this last one. I don't know. What do you think? I don't know. They both have pros and cons, I guess, right? So I was doing this problem, and look at this. When I plug in X equals 0, the electric potential is non-zero. Do you see that? So again, if you plug in X equals 0 in this equation, do you agree the answer is not 0? That's a problem, because if you have a minus charge here and a plus charge here, what should be the answer when you're right at the middle? V equals 0, right? So this is something I discovered. And the issue is, if X is less than A over 2, you need those absolute value signs. So I just wanted to point out, it's very easy to believe your equations are correct, and then they're only valid for certain ranges of, let me say it like this. I'm trying to point out something I worry about you guys doing, and this is it. Look, in the original picture, we assumed X was bigger than A over 2. That means any answer you get is only valid if X is greater than A over 2. If I go and check it at X equals 0, it might not be valid. In particular, if we don't include these absolute value signs, there's no reason to believe our answer should be correct at X equals 0. I think that's enough on that, but does anyone have any questions about that? This is the main thing you should learn. Add the two voltages together, get the Qs, get the Rs, plug it in, piece of cake. That's the main thing you should get out of it. All that extra was fun math. All right. All right. I'm going to go back to the question. All right. Okay. If you're interested in seeing a binomial expansion, here's one. So again, remember, that's not something you want to focus on, but if you're a chemistry major or physics major or electrical engineering, maybe you want to try that at home. So the binomial expansion, just to remind you, is this stuff right here. Oh my gosh, there it is. Come on. Whoa. Whoa, I lost it. All right, I lost my binomial expansion. Where'd it go? Huh. Looks like I lost the other parts. I'll have to go reprint that. So for some reason that's looks like there's a printing error in the file. All right, that'll give me something else to do. I'll write that down. Reprint chapter 24 solutions. Always something. 24.2 D through whatever. All right, so I'll get that tonight. But if you want to see the rest of that, that's great. Okay. That's enough said on this problem. All right. Let's move on. All right. There's a good problem to practice. This is one that we discovered last year was actually really good to go through. I think this might help with some of the various things we're trying to learn. So up until now, with this chapter, we've been looking at stationary particles and figured out the voltage or the electric potential energy or things like that. So really what we want to do is we want to make things a little bit more dynamic, and we want to analyze the motion of things and use the potential energy or the electric potential, again, U or V, to help us understand this stuff. So what I want to do here is I want to describe, I want to do things the old way here, right? And what we could do is we can figure out all this stuff using chapter 21 stuff, force, and we could do work, etc., all this type of stuff. All right. Now, then we can go back and we can figure out what happens if we do electric potential energy. So let's go through this one really quick. All right. 24.4. All right. So we've got a plus plate here. We've got a minus plate here. 1, 2, 3. And then we've got a charge inside. All right. It's a proton. Okay. And it says V initial equals 0. All right. Whoops. Okay. So to be clear, V initial, notice this is not a capital V. This is a lowercase v. And we're going to see this a lot in this chapter. Capital V means voltage. Lowercase v means speed or, yeah. Okay. So in this case, oh, and I have the questions open here. Let me get to it. All right. We have an electric field inside. 1,000 newtons per coulomb. All right. And I know the spacing on these plates, I'm going to say is D equals 5.0 centimeters. All right. Should the electric field be constant inside of two parallel plates? Do you remember from last time?
I think it's yes.
Yes. So that's why you might be saying, well, wait a minute. If I'm closer to here, isn't the electric field going to change? For this problem, the electric field we're going to assume is constant everywhere in the middle of this plate region. It might be non-constant like way out here at the edge, but in the middle, it's basically constant. Okay. All right. So in this case, we are asked to determine the force on the particle. How do you get the force in this case?
Q times the electric field.
Yeah, Q times E. Do I know the charge on a proton?
It's just Q.
Yeah, which is E, right? E,
Yeah.
a 1.602 times 10 to the minus 19. All right. What's the electric field? We've got it. What direction is it? What direction is the electric? Yeah, it's from plus to minus or from high voltage to low voltage. So we expect the electric field points this way, right? All right. So if you wanted to, you could even throw in an I hat on there and stick a vector on it. These numbers you could plug in, done. Let's go to part B. Determine the work done. How do we get the work done? Does anybody remember any equations for work now that we know the force?
There's the integral
Force
of
times distance.
Okay, it's the integral of F dot ds. But if your force is a constant, doesn't it just pop out? So it's force times distance times cosine of some angle. I think both of you were right there. I think, was that Joseph and Esteban there?
Yep.
Yeah. So what's the angle between the force and the direction you travel, though, in this problem?
0.
0, right? Because isn't the force, now to be clear here, this is a proton. So the force on it should point the same way as the electric field. So we'd expect in this case, the angle is 0, which means cosine of that angle is 1. So that's I think where Joseph was coming from. He's like, yeah, it's just force times distance in this problem. And this would also be correct. So in this case, oh, whoops, this is still part B. I think if we work all this out, shouldn't it be E times D? The I hat will go away because, right, there's a dot product. We no longer have a vector. So after all of this, right, this should just be E in the I hat dotted with D in the I hat. The I hat dot I hat is 1, and we get E D for this problem. All right. So far, so good. Any questions about that? Just unmute if you have a question and just shout it out. I'll stop at any time. Okay. For part C, final kinetic energy. Any ideas where I would go with that one from physics 1? I just talked about force and work, and now I'm asking about kinetic energy.
K d squared.
What's that?
K times distance squared.
I don't know. That that may relate to it, but that's not where I was thinking of going. I was trying to think, how does work relate to kinetic energy? Oh, Darren, I just saw your chat now. That tells you how slow I am. Okay. Oh, there it is. Work. Okay. So he's got it. Work equals actually delta KE. Okay. So I'm looking at the chat now. And so actually that's equal to minus delta U. And I think that's what you were thinking of, Darren. So remember that the change in kinetic energy is opposite the change in potential. And then work is, yeah, okay, got it. So take a look. In this case, what was the initial kinetic energy?
Zero.
0. So do you agree in this case, it's equal to K final minus K initial? That's 0, right? These are kind of like our chapter 7 problems. So in this case, that is 1/2 M V final squared, right? That's going to equal the work, which was E D. From there, I think you could solve for V final. Agreed? We know this. Solve for V final. What do we get for that? Let's see. V final equals the square root of something. I got to think here. What is that? 2 E D over M. And just to be clear, I'm going to, it's not the mass of the electron. This is a proton, right? So it should look something like that. Make sure I didn't screw it up. 2 comes over, and yeah, square root. Now you might be saying, do I need to worry about the plus or minus? In this case, which root seems appropriate for this problem?
Plus,
Plus, because we're going to the right. So in this case, I would select the positive root because the final velocity is going that way. If I just wanted speed, then I know I would take the plus and I wouldn't even write these. All right, so just so I have a little bit of room here, I'm going to put this result up here. So we said work equals delta K, and that led to the result V final equals the square root crap, 2 ED over M of a proton. All right, that's part C, I think. Oh, whoops. I just did part C and D. Do you agree? One of them was just get the final kinetic energy. Well, the final kinetic energy is the same as the work. So this is part C and D. Sorry about that. My bad. All right. Okay. And now part E. This is subtle. It says, get the potential difference between the plates. So this is something I want to focus on in today's lectures. So what does potential difference mean? Part E says potential difference. What is the symbol for potential difference, do you think? And you can do chat or unmute. I'm watching.
would it be delta V?
Mm-hmm. And that's something I wanted to be very clear about. It's delta V, not V. Potential is V. Potential difference is a change in voltage. When you read the label of a battery and it says 1.5 volts, what that means is there's a difference between the plus and minus terminal of 1.5 volts. So you're actually reading delta V's when you read batteries. So this is a delta V. Now, I'm just going to tell you this fact. It's written on the back of your equation sheet somewhere. I'm going to show you where this is. This is a fact I expect you to just know for the rest of the class, and that's part of the thing. Right here. For parallel plates, you're supposed to know it's either sigma over epsilon naught, or if I'm talking about voltage, it's the change in voltage over D. Notice I got absolute values here because this is not a vector, right? So in this equation, the electric field magnitude between the plates relates to the size of the potential difference divided by D, okay? Sometimes I remember that as V equals ed, but yeah. So in this case, we know the size of it is equal to, what was it? E times D, right? Okay. So questions about that? Let me get a little bit less glare. All right. All right. Now there's always going to be some glare. Sheesh. Trying out the new lighting. All right. Okay. So let's go to part F. Okay. So this is something. Oh, go ahead.
Sorry. Can you
Yeah.
explain that again? Why is it E times D? I'm sorry, I missed it.
Because the equation on the back says E for parallel plates says delta V absolute value over D, where D is plate spacing. Sorry, I didn't make that clear. So in this equation, it turns out if you know the voltage and the plate spacing, from a practical standpoint, you get the electric field that way all the time in a lab class, right? If you know you could change the power supply voltage, you could change delta V, and remember those metal plates I had, you could change the spacing. And so you could actually control the electric field very easily by knowing voltage difference and the distance between the plates. Is that enough on that?
Yeah.
Yeah, it's just a new thing that I want to use because we see it in labs sometimes, and it shows up in a lot of problems throughout the rest of the semester, it turns out. And this is only, I should point out, for parallel plates. This isn't true for point charges, right? The electric field for point charges is not constant in between. This constant value is only true when we have parallel plates, right? So this special formula only applies for parallel plates, but parallel plates are used a lot in the real world. That's enough on that. All right. Okay. So part F. Oftentimes we say the negative plate is at ground. So sometimes what we'll do, if you see an electronic schematic, what they'll do is they'll say this. They'll put a triangle like this. This means ground. Or it means voltage right there is 0. So if we say this plate is at 0, this plate must be at plus V, where V is E times D. So the voltage at this plate is actually E D in this particular problem. All right. So yeah, that's what ground means. Ground means the spot that is 0 voltage. Now, if you're worried about this, think about back when we did gravitational potential energy, right? You could say in the problem, the bottom of the problem is 0 volts, or you could say the top of the problem is 0. I should be careful. You could say the bottom of the problem had 0 potential energy, or you could say the top, or you could say any point in between. In gravitational energy problems, back when we lifted boxes and threw things around, you could choose the 0 level. That's the same idea that we're doing right here. Remember, this voltage is a lot like the height in the topo maps, right? Remember the maps that we were showing? So in this case, you can arbitrarily set any one voltage in the problem to 0, and then every other voltage in the problem is referenced to that level. That's what ground means. Just like normally we set gravitational energy equal to 0 at the ground in a problem. All right. All right. Questions about what ground means? It's just what reference level we choose to call 0. It's arbitrary. If you remember, you might be saying, well, wait a minute, can I just flip this stuff around? If you remember back in the day, what matters in real problems was changes in U, right? Changes in U is minus delta K. The actual values of U itself never appear by themselves. They always appear in initial and finals in any real problem, right? You always have a U final minus a U initial. Well, if you shift everything by 5 volts, right? That's the same thing as shifting all these potentials by something relative to 5. Right? So if you shift all your energies by 5, the plus 5 and plus 5 in each term is going to cancel out. So you could pick any value you want to be 0 in these problems. Now, when we're doing electrical problems, remember that for electrical problems, delta U is Q times delta V, right? If U is equal to Q times V, then delta U is Q times delta V. And the idea here is, think about it. If we add 5 volts to every term, and in reality, we're going to add that to both the initial and final voltage, who cares? Because it's going to drop out in the deltas. Is everybody okay that we can call wherever we want ground now? I don't know if that makes sense.
So basically, it doesn't have to be 0 volts. It could be like 1.5 volts and just call it 0.
Yeah,
We're just looking at the difference.
exactly. So if I could, let me put some numbers on this. All right. And just so this relates to these problems, let me check the numbers in this problem. Hold on. Okay. What was this? 24.4, right? Oh my gosh. Okay. I got to reopen my solutions. Oh, geez, whatever. All right. I'm going to do a simple problem really quick. All right. Just so I'm not getting hung up on this. All right. Let's say delta V is equal to 6, just to keep my life easy, right? You could have a 6-volt lantern battery. All right. I could say that this side's at 0 and this side's actually, let's say this was the plus terminal and this was the minus terminal. I could say this is at 0 volts and that would make this one at 6 volts, right? Or I could say this is at negative 3 volts and then the other side would be plus 3 volts. These are the two most common ways you'll see it. You'll either split the difference so that 0 is right in the middle, or you'll put the negative terminal at 0 so that the positive terminal, and then we don't have any negative numbers in here, right? Or like, you could put it anywhere you want. You could say this is negative 1.5 volts, and then that would make this plus 4.5. Or you could make this negative terminal positive 1.5 volts, and then this would be 7.5. Basically, you could call whatever number you want 0. And then what matters here for parallel plates, what I'm trying to emphasize is just the change in voltage is what matters here. Maybe that's overkill. Good on that, Esteban?
Yeah.
Right on. Okay. Any other questions on that?
Are there any like tricks that we can use when it's not parallel plates?
Nope. Not that I have, right? Yeah. I don't have a quick one for you. Yeah. In practice, if you have non-parallel plates, you have to go back and either code it and figure out the voltage with coding, or you could do calculus. We could show how to do that later in class. Like, remember, you could do something like this. The total voltage is equal to the integral of K dq over R, and do an integral like that and add up all the little pieces. You could write a code that does that for you, or yeah. So if you have non-parallel plates, basically we have to do something harder. Is that good?
Yeah, so this works like pretty much the same as like gravity as far as like picking the points and just finding the delta.
Yes. The only difference from this and gravity is there is a major problem that's very subtle. Charges can be positive or negative. Whereas before, when we did gravity, mass was always positive, so we didn't have to think about that extra aspect. Now it gets complicated because charge could be plus or negative, so you could get some cancellation, right?
Oh, okay. So it's kind of like you can change like up and down, like kind of like talking about gravity, but
Mhm.
going to like electric, you can kind of change which way like the object's gonna fall, I guess,
Yes,
or the charge is
Yes.
gonna fall. Okay.
absolutely. So like in this case, the charge is falling to the right. Agreed?
Yeah,
Yeah.
that's
And
cool.
so what if I flip the plates? The charge would fall to the left, or you could make it fall upwards or downwards, or et cetera, et cetera. Good?
Yes, thank you.
All right. All right. Now, okay. I'm going to go ahead with part G now. I'm looking at part G. It says, in this problem, U is the electrical potential energy of the proton plate system. So notice it's not stored in the proton. However, from a practical standpoint, we don't expect the plates to move much compared to a single proton, right? Plates are basically infinite mass compared to a proton. So the plates are going to sit still. So you could argue, well, in this case, the proton has all of the potential energy, even though it's stored between the plates and the proton. Okay. All right. So in this case, determine the electric potential energy of the proton. So I'm just going to show you this a little bit different way now. So I want to erase this problem and just show you a different way of doing this type of problem. And I think you'll see the advantage. This is a lot of remembering old stuff, right? All right. All right. So in this case, imagine, and let me get this electric field out of here too. Just remove the clutter. So let's start this problem over. We've got these two parallel plates. Your velocity initial is 0. Let me get this over here and bump this up. All right. We're going to set this side to ground, 0 volts. This side was at voltage. What did we say it was?
ED.
ED. Thank you. And that was a capital E times D. So, right, these are numbers we could plug in and get a value for that. Did anybody happen to get a value for that? If you did, cool. All right. Now, watch this. I could do this problem this way. I could say K initial plus U initial plus work done by non-conservative and external forces equals U final plus K final, right? And that's what I wanted to show you today. Instead of doing all that other stuff, which we can do it, this is a little bit faster. The initial kinetic energy is what?
0.
0. The initial potential energy is Q times voltage initial. In this case, I'm just going to tell you right now, electrical forces conserve energy. Great. So we don't have anything else. Do I need to worry about gravity in this problem? What do you think about gravity acting on a proton versus a Coulomb force acting on a proton?
Negligible.
Yeah, gravity is completely negligible. So you might be saying, dude, you need to put in an MGH. No, it turns out the gravitational force is completely negligible compared to this massive. So, right, there's 0 there. Good. This would be Q V final. And now notice here, I want to be clear. I'm trying to be super anal about this, whether I say a capital V versus a lowercase v. So if I know the voltage initial and the voltage final, I could crank this out in one line. And it's so much easier than doing all that other stuff. That's what I want. Oh, go ahead.
The voltage final is 0, right? So you can just
Yep.
take that out.
That drops out. So notice this gives me Q E D equals 1/2 M V final squared. Well, Q in this problem is lowercase e. We get back the same answer that we had before without having to remember dot products, angles, work definitions, deltas. It's like, oh my gosh. So this is how we might start to do some problems now. Rather than doing forces and work and all that stuff to get through this, why not just say the initial energy equals the final energy? And then maybe there's a correction if there's friction or something, but I don't think we're going to have that very often. Most of the problems in this chapter, there's no external work, right? We're not going to talk about air resistance on a proton and things like that.
So
All
this,
right.
this only works when the energy field is constant, right? So it wouldn't work. if
No.
it's-
What's cool is this works even if the electric field is non-constant. Isn't that sweet? So even though we only did this for parallel plates, so I basically, here's what I did. I used the parallel plate problem to show you this is equivalent, right? What's cool though is this procedure works even when we don't use parallel plates. You could do this for point charges. You could do this for weird stuff, other things. That's powerful, right? Now we could do a lot of problems where we don't know the force, or if the force is not constant because we have point charges and it's changing all over. We could still do this, and maybe you can't get the time out of this, but you could get the final speed. So that could be useful stuff. Is that good, Esteban?
Yeah.
Yeah, so there's a use to this. All right, should we try another problem? I'm going to, let's do 24.5, okay? Oh, wait. There was one more part H. I forgot about part H. Let's say we started with an electron at the negative plate. So part H is basically the same thing. And I think there was some stuff that we encountered here. And there is something subtle and important in this. Otherwise, I wouldn't be wasting my time on it, okay? Okay. So in this case, what if we started with an electron right here? All right. In this case, would the electric field inside the plates change? If I put an electron over here instead of a proton there, is the electric field going to be different?
No.
No. Is the force on the charge going to be different?
No.
Yes.
Hmm.
The magnitude is not going to be different.
I have
But
to just push to
remember-
the right.
Remember, check this out. Force is equal to QE, right? If you flip the sign, you flip the vector. Well, I should be careful. If you flip this sign, you flip this vector. The electric field doesn't change, but the force would flip directions. The size of it wouldn't be any different. Are you clear on that? That subtlety?
Yeah.
All right. So what about the work done? Would the work done be different?
Same force, same distance, right? So now, I mean, it would be the same.
Yeah, take a look. If we go to the integral, you could see it a little bit, right? The force flips direction, but so does the direction the object moves. And so these both flip, so then the work doesn't flip. Okay. Okay, what about the change in energy? Would that change? What do you think? How does work relate to the change in kinetic energy? If the work doesn't flip, do you change the kinetic energy?
No,
Would you change the final speed?
no.
Yes.
Oh,
Why? What's different about a proton versus an electron?
the mass.
The mass. Which would be going faster? An electron going this way or a proton going that way?
Electron.
Electron, right? Because there's a 1/2. Right? If the mass goes down by a factor of 2,000, what's going to happen to the speed? It goes up by what factor? Square root of 2,000. I don't know it either. Good. I'm glad you didn't say 2,000. Right? The idea is if the mass goes down by 2,000, the speed should go up by, since it's squared, the square root of 2,000. All right. All right. So just watch out for this type of stuff. There's a lot of stuff in these problems when you're doing them. When you flip signs, sometimes you get multiple sign flips, sometimes you don't. And then sometimes, even though the charges are the same, the masses could be different. Every once in a while, the mass matters, especially when we start getting kinetic energy involved. So just be aware there's a difference between kinetic energy and speed. They're related, but there is a mass in there. That's enough on that. Now let's get to the next question. Oh,
So
go ahead. Any other questions on this? Yes.
Forces it just becomes equal and opposite, but velocity changes, or sorry, yeah, velocity changes in like that it increases in magnitude.
Yes, we would expect the electron, which is 2,000 times less mass than a proton, should have square root of 2,000 times more velocity. The velocity should go up a lot.
Okay, but the force should be equal in magnitude, right? Just
That's right. And so you could think about it this way. We know that force equals ma. Well, if you have the same force, smaller mass, more acceleration.
Okay.
Is that good?
Yeah.
Yeah. All right. So watch out for protons and electrons. A lot of things end up being the same, and sometimes they're exactly opposite. Yeah, whatever. Okay.
Why did you do square root 2,000?
Because it's v squared. Look, if this v goes up by square root of 2,000 and then you square it, you'll get 2,000 here, which will cancel that 2,000 there. Is that right? If the mass goes down by 2,000 and each of these velocities goes up by root 2,000, you'll have 1/2,000 times square root of 2,000 times square root, and it'll balance.
Okay.
Is that good?
Yeah.
Yeah. I just wanted to stress that just because the mass goes down by 2,000, we don't expect the speed to go up by 2,000 because there's a square in there. Do some paper and do some math. Is that good enough?
Yes.
All right.
Yeah.
All right. Yeah. All right. Let's take a look at 24.5. Okay. And I'll bring it up on screen while I'm drawing it. Actually, this would be a good time to take a short break. I just looked at the clock. It's actually, let's try and get this problem done, then take a break. Okay. This one's pretty quick. Well, famous last words, right? Let's look at 24.5. All right. Oh my gosh, what is going on here? I'm getting some weird stuff. All right, whatever. I think I need to reboot my machine. Look at it, 24.5. I'm just getting it drawn up. Just getting it on my whiteboard here. Okay, we've got spacing, we got masses, so they're electrons. Okay. So I'm going to go ahead and stop the share and look at my whiteboard. So I've got 3 electrons here. They're all at rest. They all have the same mass, which is the mass of the electron. They all have the same charge, which is negative E. E is the magnitude of charge on the electron. So all these have Q equals negative E. All right. Let me ask you something. You put all these things together. What do you think would happen if you release it from rest?
Shouldn't the middle one stay put and the left and the right shoot out to left and right?
That's what we expect, right? So do you think this has a positive or a negative potential energy right now? It has the potential to shoot these things out, right? If it's going to cause these electrons to move away from them, we would expect that this has a positive potential energy. Okay. Now we might be worried about this minus sign. So that's what we're looking at here. Now let me read the question here. It says, determine the initial energy stored. So let's see. I think it should be positive. We'll worry about the final state in a minute. So what is potential energy? What's the symbol for it?
U.
U. So now we're talking about U, not V. The last problem we showed how U and V were related. This problem we're talking about U. Does anybody remember how I'm going to get U for these 3 point charges?
Do U 1 on 3 or U 1 on 2, 1 on 3, and then 2 on 3.
Yes. So there's 3 pairs. So we need to get all of these 3 pairs. So maybe I'll label them 1, 2, and 3, just so it's clear, right? It doesn't matter which ones you label because they're all negative now. So I would say this. Now, in this case, and I'm going to go down here. What is U12? Well, that's going to be K negative E times negative E divided by what's the radius between 1 and 2?
A.
Sure thing, eh? Don't you know? Canadians' favorite distance, eh? How about 1, 3?
Same thing, but 2A.
Yeah, and do you agree the negative times the negative is just going to end up being KE squared? So we see it is going to be a positive. Just take a look. I'm just cheating a little bit. So this one's a 2A. And then the last one between 2 and 3 is distance A again. If we add all this up, what do we get? Well, there's going to be a K E squared upon A times 1 plus a half plus 1. Right? Well, that's 2.5. And I should pause for a second. Is everybody okay? That's how I could get the initial potential energy. Instead of doing KQ over R for point charges, that's voltage, we have to do KQQ over R. So potential energy, there's an extra charge in there. The potential energy is stored between pairs. And so I'm going to go ahead and write that up here just so I don't lose it. So there's our answer for that one. There's the initial. So that was part A. Okay. All right. I'm going to erase this. And I want to read the question again now. In part B, let me bring it up on screen. What is going? My computer is like melting down or something. Okay, whatever. Okay, so Esteban was correct in his first assessment that if we release all three of them from rest, we expect the one in the middle to sit still. But now we're told we're going to hold two of them in place. So we're going to take these two and we're going to pin them. So these two are fixed. So if that's the case, what do we expect to happen to this one? The one on the right.
Shoot off to the right.
So we expect these two are going to sit here. They're going to be in the same spot. And the other one is going to fly away and be moving while the other two are not moving. And to be clear, that V is a lowercase v. That's what we expect the final picture to look like, right? So now what I want to do is determine the speed of that thing when it gets far away. What's a good name for this distance right here if it's far away?
Infinite.
Yeah. So what we're going to do is we're going to get lazy as physicists and say that that distance is r equals infinity. Technically, I should say r is r and then take the limit as r goes to infinity, but I'm not going to do that because I'm lazy. All right. So let's go back and take a look at how this affects the problem. Oops. So now in the final state, we expect to have an electron here, an electron here, and then we have another electron way over here. We're told that this distance is essentially infinity. That's what it means by very far away. So if I want to get the speed, what type of problem could I do? When I ask about speed, do you think do forces and kinematics or do you think do energy?
Energy.
Energy. So what do? I know U initial plus K initial equals U final plus K final. We're ignoring the work done by external and non-conservative because we expect there's no friction and stuff like that. This term is zero, right? The initial kinetic energy is zero because they were all at rest. The initial potential energy, I got that from the earlier work. The final kinetic energy is going to be 1/2 mass V final squared. So all we need to do is figure out U final. What's U final in this case? Zero or non-zero?
Say 0.
And that's what everybody says. And that's what's wrong. Why is that wrong?
Because if you plug in U initial and then the kinetic final, you move things around, you find out that UF is not equal to 0.
Yeah. What part? What do we do every time you have three charges and you're trying to figure out the potential? We do U12 final plus U13 final plus U1 or 2-3 final. Now remember, this is number 1, this is number 2, and this is number 3. These two terms are 0 because those are really far away, right? Is this 0?
No.
No. In fact, what is U12?
The same as the first one.
No. Well, oh yeah. The same as the first one for 1-2 only, you mean?
Yes.
Yeah. Sorry, my bad. Which is just this, right? And so the idea is U final. Oh, okay. I'm getting kind of sloppy here. This is going to be U final. U initial was that other one that we figured out early, the 2.5. So we have a 2.5 KE squared here. And I just wanted to point that out. When we have point charges moving around, sometimes the final potential energy is not 0 because you have to consider all pairs. And if one of the pairs is still floating around, you got to deal with it. So far, so good?
Yeah, I assumed there was zero because I was thinking like gravity, and I was thinking of just two masses and how it goes to zero.
Yeah.
But
So do you agree you could have the same thing with the 3-mass system?
Yeah,
Or,
yeah.
you might have some. And so this is where I was trying to say the energy. This goes back to your question earlier, Esteban. The energy is stored between all three somehow, and some of it is kept right there because these still have the potential to move if you release them, right?
Mhm.
What's interesting is letting go of them all at once versus first letting go of that one, then letting go of this other one is different,
Mhm.
right? And so it depends on the way that, so there's no good way to say the energy is stored at a point or with a particle. It's in the entire ensemble.
Yeah, that makes
Yeah.
more sense now.
Yeah. And it'd be interesting to do this problem. You could compare what happens if you just let one of them go, then at a much later time let go of this one. You'd have to do 2 energy problems, and you could compare the final speeds of this one versus just letting all of them go at once. Well, if you let them all go at once, right, this would be very similar, except you'd have 2 of these terms here, right? If you let them all go at once, this one wouldn't move. These 2 would move. And if both of these move out, then U final would be 0 because these would both be infinitely far away. All right. All right. Let's take a look at something else here. Oh, we should take our break now, but I'll end with this comment. Oh my gosh. Yeah, it looks like I got a, this looks very similar to this problem. Let's talk about this when we come back. I'll reboot my computer and get rid of this stuff. So, oh, I don't know if I can, I'll just reboot my, yeah, I'll leave the Zoom running. All right, let's take a 10-minute break, everybody. 10-minute break. Let me see if I can fix this crap. All right. Oh, how's everybody doing? What do you think of Zoom today? Maybe you're still on break.
I'm not sure if this is happening to everyone, but when clicking on your join link through email,
Yeah.
for some reason it downloaded under Zoom exe file, and
Huh.
I don't know why.
Hmm. Yeah, I don't either. Yeah. Yeah, I don't know. I know some of you kind of came in late and maybe you didn't see the announcement I tried to send out. My goal is not to do Zoom that often. Yeah, I've been told by the school I need to decide some things, and so I don't know. And I moved a lot of stuff around. I'm trying to check out all my systems before I make a complete decision. So yeah, it's a lot easier on a full whiteboard, right? So I got to tell you, I'm curious. I'll see if I can look up the stats from your guys' survey. It was pretty funny, but it hadn't been full survey results yet, so I'm curious. I'll see if I can bring that up. Where is it? Still not used to the lighting in this room, and I don't know. How's the connection today? Is it mediocre to okay? Or is it cutting out all the time, or
It's fine for me.
been doing all right? Yeah. Okay, we got 34. Let's see what the surveys say. I think I have to click a button here. Let me see if I can share that. Let's see. Hopefully you're looking at the screen. So this is what I've gotten so far. And I think this is, as you can see here, this is 34. So this is not the entire class, is about little over half, is about 2/3 of the class responding. So it looks like most of you are probably less anxious about COVID than I am, right? I have unvaccinated children that concern me. So, right, they can't get the vaccine yet. I think if my kids could get the vaccine, it would really relax me a little bit, but I'm still a little freaked out. But this kind of tells you, it looks like most people like all face-to-face. That's not true. Some people are okay with the lectures being on Zoom, but yeah. All right. Anyways, just curious. Does anyone actually watch the old lectures on YouTube? Has anyone watched any? I'm just curious if any of you had.
Yeah, I actually watched a couple, but mainly they're for like the old labs and stuff. That's what I was watching.
Oh, like the coding videos, right?
I watched a few of those, and then I watched one of them on electric potential. But other than that, I just been watching the lab.
Yeah, we've been in face to face, right? Yeah, I'm curious personally. I wonder if the Santa Maria Elks Rodeo is going to be a super spreader, but right? It's outdoors, but what do everybody do right after a rodeo? They're all going to get drunk and go hang out at the bar. So I'm a little worried about that for like the next 3 weeks. That's, to be honest, probably the biggest source of apprehension. So I don't know, when we're in there, you guys have been pretty good about being masked up and stuff. So, I mean, that's the thing. If I see that starting to slip, it's like, man, I like you guys and I want you to have a good educational experience, but I'm not willing to kill my children for you guys. You know what I mean? That's what that's what weighs on my mind when I'm in there, and I'm always thinking about it. It's like, I don't know. It's probably total, right? It's probably not that big a deal, but you can't help it as a parent. You freak out about your kids, right? So I don't know. Right. Just imagine my kids get long haul COVID somehow, right? And I know the statistics, I know it's unlikely, but it's still a chance. And so it freaks me out. I don't know. That's where yeah, it worries me sometimes. So yeah, I appreciate that you guys are all considerate in class and do the masking, because if that wasn't happening, I'd be like, fuck this, I'm out of here. Anyways, all right. Let's get back in and do some more work. And let's see if we can get to, let's see, I think I reopened these files. Yeah. All right. So I wanted to talk a little bit about this one, 24.7. All right. So this is a variation on the previous problem. Imagine you have a proton that is initially moving, and then it's going to come close to basically a nucleus or something, right? So if I could, imagine you have this, you could have U initial is approximately equal to 0 when these two charges are far apart. And U final would be something non-zero. It'd be K Q1 Q2 over the distance, right? Now, in this case, the kinetic energy initial is essentially 1/2 mv squared. The kinetic energy final is 0 because it's at rest. And so this would describe a charged particle flying towards a nucleus, and it comes to rest. Obviously, right afterwards, it would rebound and go flying back out. I hope you agree with that. So it's going to fly in, come to a rest, and then right afterwards, it would shoot backwards. You could do the math. Basically, you're setting this term equal to that term, and you could get the distance of closest approach. And when they did this, they were able to get a size limit on the nucleus, right? So if you're curious, that I alluded to this before, Rutherford scattering, and they actually did this with alpha particles, and they shot this. And here's the actual quote, I think, or something similar to this. The quote was, it was as crazy as if you'd shot 15-inch shells at a piece of tissue paper and they bounced back. That's how insane it was when they first discovered this happening. And they discovered that the nucleus actually is a small positive charge. They used to think it was a negative charge at the center. Now, here's another quote, which I just find insane. All science is either physics or stamp collecting. And then you can see my retort. Why do people say physicists are arrogant? I just don't understand. Anyways, I thought you'd get a laugh out of that. So there's a practical application of this, right? This was used to determine the size of the nucleus, or at least put an upper limit on its size. All right. That's good. If you wanted to, here's a variation where you have these types of charges. So if you're curious about how might I do a test question for some of the stuff we've been talking about today, you got these point charges here. You could either have all of them move, or in this case, you could say, here you have 4 point charges moving. So notice it's the same type of thing as this problem, where here they were in a line. So on problems 24. I think it was 6 and 24.7, they were all in the line. You could use a square geometry, do the same thing. K initial plus U initial equals K final plus U final. All right. You could do the triangle geometry. And notice this shows you some ways I might mix this up on a test. Compare problems 24.10 and 24.11. Right? If you release the top charge from rest in 24.10, which way is it going to go? Well, let's look. They have identical negative charges. So this is negative, this is negative, this is negative. When you release this top charge from rest, what's going to happen to it?
It's going to go straight up.
It's going to go straight up. So this looks like an escape problem, sort of like the first problem we did where it flies away. What if this one's negative, this one's negative down here in the lower problem? So now we're looking at 24.11, and the top charge is positive Q. If this is positive, what would happen if you release it from rest?
Straight down.
Straight down. Where's it going to hit max speed?
Right before hitting.
Is it going to stop when it gets to right there?
Is that the max speed right there? Because then it's like passes that point and they start pulling it back.
Exactly. So once you go past this point, so on this way, the force is downwards here, right? So you're doing positive work. You're speeding this thing up. Whereas here, the force is negative, or I should be, the force is opposite the motion, right? So here, the force and dx or ds vector are pointed the same way. When they're pointing the same way, you speed up, right? Whereas here, you're moving downwards, but the force opposes your motion. You should slow down. So where will it stop? You release this
will
from
it
rest.
stop
Yeah,
the same point downwards?
exactly. When the
As it
triangle is
started?
flipped upside down.
Yeah.
All right. Now, do you think this equation is valid? Do you think we could describe the position as some cosine function? What do you think? This is a challenge, so just take a guess. What does your gut tell you?
Yes.
You would think that, and I suspect it is not true. Now, here's the deal. I don't know if you know this, but if you're going to learn this in Physics 162, right? Let's go to the whiteboard for a second. Right? Let me get me up there. All right. I guess I should have cleaned this whiteboard. All right. Yep. Now, where'd my markers go? Right here. All right. So in this case, now I forget what I was doing there. What was I talking about? Shit. I was looking at,
Position.
oh, A cosine omega t. Yeah. Okay. So if we had a minus sign and a minus sign here and a plus charge here, we know this thing is going to oscillate back and forth between these two positions, right? But the thing is, if you look in Physics 162, there's an equation. We know that minus kx equals ma. This is for a spring. We did this in 161 as well. And so if you look at this one, maybe you know this is minus k over m times x equals dx squared dt squared. Or sometimes we'll say that's x double dot, 2 time derivatives. Okay. In this case, only when we have this situation do you get a cosine function out. If you have 2 derivatives equals a constant times the position. And I don't think we have that, because what we have is some complicated formula here that has k q over, there's like, what is it? It's going to be like a over 2 quantity squared plus y squared quantity to the 3 halves. Give me a sec. Right? We're going to have some big ugly mess from the Coulomb force like this, and times 2, and there's maybe there's a y up here. It's complicated. Only if y is a very small number will this be simple harmonic. If y is a large number, the force is changing wildly. And only when we have a force that's got some spring constant like this, if it's a linearly changing force, we would expect simple harmonic motion. Short end of the stick is I see no reason to see why this force will change linearly if you have a large value of y. So if you know what I'm talking about, great. If you don't, who cares? Let's move on. You can learn about that in Physics 162. Not all oscillations are cosine functions. Done. That's all I wanted to say about that. All right. Where did it go? Come on. Locking up. Let's try it again. There we go. All right. So what's going to happen if the alignment isn't perfect? Code it. Enough said. All right. Ooh, oof. All right. Now, we've done enough problems like this already that I don't want to do this one right now. But if you are a physics or a chemistry major, this is a crucial problem for you. This is used all the time. So this is showing, it's kind of an extension of that one that we started with where we talked about Lompoc and Napomo. Those 2 points were on axis. This one shows you what happens for an arbitrary point. And it helps you, you could see the binomial expansion we'll derive the dipole potential that is used all the time in chemistry. So a dipole is basically two charges separated by a small distance. If you're a chemistry major, perhaps you know what the dipole moment is, or you've seen tables of dipole moments that relates to this problem. So I think that's enough said on this problem. This is basically, you could do that one. All right, equipotentials, we're going to work on that in lab. So let's worry about lab in lab. Okay. Ooh, page 70. This might help you a little bit. If you're doing your pre-lab, maybe you should look at this. All right. I think this is a pretty good idea. That might help you. All right. So page 70 may be useful in your pre-lab. I think you get 2 shots on the pre-lab. So I would try one tonight. And then if you screw up, then you could do it again. All right. All right. Let's worry about this later. All right. I'd like to get into continuous charge distributions now. So I'm going to start with 24.18. All right. I'm going to get my whiteboard ready. Oops, 18. Sorry. And I bet you probably already finished the problem. You're faster than I am, right? Just drawing it out. All right, I'm ready for the whiteboard here. Okay, here we go. We're trying to get, I believe in this problem, aren't we trying to get the electric potential? Is that what it said? I forgot to write down what I'm looking for. Determine electric potential. What letter is that?
V, volt.
Yep. And now what are we going to do? We're going to build it up out of little contributions. So we're going to, the total voltage should be the sum of all the contributions. Remember, your integral is like a sum. Well, what's dV for a point charge if you had to guess? What's the equation for V of a point charge? KQ over R. What is dV?
K dq or R.
Yeah, piece of cake. Do I need to worry about any vectors?
No, because R is magnitude.
Yeah. So this is a lot easier than what you did before. All right. So all I need is the R vector. Now, what does R mean, right? R is from what to what?
POI to
It's always from the to the
source to the POI.
yes. And then because it's an R vector, you could slap on an absolute value on that, right? Sorry, because it's an R magnitude, we could slap on the absolute value. I misspoke. So in this case, what is R?
Just X.
X. What is DQ? What was it in lab all last week?
Lambda dV.
DX, or some kind of small increment, right? This is coulombs per meter times meters, right? So I get coulombs is equal to the coulombs per meter times an amount of meters. Can't you just shove that all in and hit go? What are the limits in this case? What are the limits?
From A to A plus L.
Yes. R goes to X. So in this case, all of this is just X. Right? All right. So in this case, what do you get when you integrate K lambda dx over X from A to L plus A?
1 over X squared. K and lambda pull out.
Nope.
No?
K and the lambda pull out. I'll give you that.
Natural log of X.
Yeah.
Oh, yeah.
So do you agree that's going to be log of the upper limit over log of the lower limit? Have you guys seen that before?
Yeah, because you use subtraction and you just switch it to the quotient.
Yeah. So you do a subtraction, but you get log of A minus log of B, which is log of A over B. In this case, A would be L plus A, B would be just A. It's kind of a, B is the new A. All right. Anyways, so there we go. This would be the electric potential. Now, what's lambda? Did I specify if this was uniform or non-uniform?
You said it was continuous, so it's uniform.
Unless otherwise specified, we would assume it's uniform, right? So it's not that I specified it's continuous. It's that if I don't tell you something is uniform, but I don't tell you it's non-uniform, we generally make the assumption that things are uniformly distributed unless you clarify otherwise. So here in this problem statement, I'm looking at the problem. I don't see anything implying it's non-uniform. So we would assume then it's uniform. So assuming uniform, lambda is
Q over L.
just Q over L, just like we did in lab. Piece of cake, right? Isn't that so much easier than the electric field? This gives us a chance to think big picture now, right? I saw something I liked the other day that I'm going to show to you. Let's go this way. Let's kind of do a review of all of physics, just really quick. When we started out, I don't know if you remember, we started out with kinematics, right? So we had X, we had velocity, X was like position, we had acceleration, right? And so if you have the position, we could go back and forth between position and velocity and figure out whatever. Similarly, we could go back and forth between velocity and acceleration and learn something that way. Well, we know that this is related to force by Newton's laws, right? And typically this is the net force, so I should be clear on that. Now, what we've done in this chapter is we've done some, well, in this class, what we've done is we've said, well, we can actually use force equals QE, and it's a little bit easier to calculate electric fields, right? Because electric fields, we don't have to worry about the charge and the sign of that charge at the point of interest. So electric fields are slightly easier here. And the idea is by figuring out electric fields, we can figure out the force and go all the way over to position and vice versa, right? Now what we're doing is we also have this extra abstraction. We agree that electric fields, we can actually learn about voltages. And if we know about voltages, voltages can tell us about electric potential energy. And these two things can also be used to figure out the velocity or the speed in different cases. And so the idea here is electric fields and voltages are so much easier to calculate. It's less confusing. It's more straightforward in the computer. So it's wise for us to calculate voltages and electric fields all the time, use that information to figure out forces and potential energies. And from that, we can figure out the motion of particles. That's what we are doing in this crap. Questions on that? Right? That's our big picture here. It's easiest for us to learn about voltage and electric field to learn about the motion of particles. And even though it's more abstract, I think you'll agree that this one is by far the easiest thing to calculate, right? So if you could do a problem this way without any vectors and then use potential energy to figure out motion, we generally speaking would like to avoid having to do vector physics. If for some reason we need to learn about acceleration, we probably need to do the forces. If you need to learn about time, right? Time is involved in all of these things. Then usually we have to get forces involved. And if you have to code it, usually we get forces involved. So that's kind of a big picture overview of where these things sit. All right, let's go back and look at another one. All right. Or questions while I'm working here. Any questions? Oh my gosh. It's not. Oops. Where'd it go? There it is. All right. You could do the same thing for a ring. Piece of cake, right? Ooh. For the ring, well, let's maybe just sketch out how you would do the ring. And since I got it here, right? Do you agree you could just take a piece of this and you could do V equals the integral of dV, right? We're going to add up all the contributions. Are we going to build up the ring out of rings, or are we going to build up the ring out of point charges?
Point charges.
So that I'm going to get a K dq over an R. What does R mean?
The square root of z squared plus the radius.
From the source to the point of interest, which is, yes, exactly what he was saying there, right? We expect R should equal, in this case, this side is what? Capital R? And then we're going to get this raised to the 1/2. You could say square root of it. If you don't know how to do that integral during a test, where would you look?
Back of the book.
Back of the book, or your exam equation sheet probably has this integral. Take a second to look at it. Yep, it's on there. Notice you get a natural logarithm. Looks pretty familiar there. Okay, so it is there on the exam in the integral calculator. So you could do this, use a table is basically how I'll say it. So you might want to practice this. But now I have this question for you. Let's focus on this question right here, part B. What do you think will happen as Z goes to 0? What value do you think the electric potential should take as Z goes to 0? How much voltage should you have at the center of the ring?
0.
Okay, what make that? That's the electric field goes to 0, right?
Yeah.
Right, because we expect by symmetry. Does the voltage have to go to 0?
No, it doesn't.
In fact, how far are you from total charge Q? If you're sitting right here at the center, what's the distance to this little bit of charge?
Capital R.
How about to the next little bit of charge right next to it?
Same.
How about to every single piece of charge? It's all distance R, right? shouldn't the final result be KQ over R? Because your distance, capital R, from the point, isn't that wild? Think about that. Does that make sense to you? If you're at the center, shouldn't we get KQ upon R? All right, I'll let you think about it. Isn't that wild though? And then, okay, what about as Z gets much farther from R? Right? If Z is really big, right? You're sitting here and you're way up here. What value do you expect to get?
You go to 0.
Or KQ upon Z, right? Which tends to go to 0. So, right, isn't the ring basically a point charge as you're far away from it? Okay, moral of the story. This part seems pretty easy. Checking your work is not easy. These things here are to help you check. Basically, those 3 parts are the ways you can check your work. This is what you need to know to pass the class, right? How to do that. These are things that are kind of like icing on the cake that help you check your work during an exam day. Is that making any sense? The checks, I think, are useful, but if you're really getting hung up on them, maybe you should, I don't know, do your math right and hope you're perfect, I guess. That's hard. All right, whatever. All right, right, you could see where this is going. We're doing the same stuff over and over and over again, except now we're doing this thing, right? So if you were going to do 24.20, kind of walk me through how we would approach this one. If we're going to build this up, V is equal to the integral of dV. We know we need to add some pieces together. What type of pieces are we going to use to build up the washer or the disc?
Out of little rings.
Out of little rings, right? So we're going to build this thing out of rings. So then what do I need to use for dV? Am I building it out of point charges? Do I use K dQ over R? What do you think?
It's not point charges anymore.
So we can't do that. What do you bet? We could look on our equation sheet and see the voltage equation for the ring. Oh, I see it there. This is on my exam equation sheet for a ring. Notice it's on the second column, 1, 2, 3, 4, 5, 6, 7 items down. That's the voltage from a ring. When I plug that in to my integral, I need to make some subtle changes. Do you remember what changes we need to do? Do I type in Q or do I do something else?
DQ.
That's right. This is not the total charge. This is just part of the charge. So it's a DQ, right? How about the radius here? What's my radius of this particular ring? Is it big R? The radius all the way out to the edge is big R, right? Is my little red radius big R? No. It's little r. So I would need to do a DQ. And now I'd have to use my ring radius. Okay. What is DQ? Does anybody remember?
Sigma.
Use the
D-
units, coulombs per meter squared. So would you need a dx, a ds, a da, or a dv? Do I
Well,
need to multiply by
DA.
meters, dA, right? Well, what's the area of my ring? That's dA of a ring. What's the area of a ring?
2 pi r.
Hold on. 2 pi r doesn't have the right units, does it? That's all the way around. That's the length of the rope if you unravel it,
Times dr.
times the thickness, right? So remember, the thickness of this thing is dr. So if you take that circle and unravel it, right, the distance all the way around is 2 pi r. And then the thickness of it right there is dr, right? So that's how we get the length times the thickness. Well, you could shove all that crap in. Take a look. You got an r, you got a dr, and you got an r squared in the basement. You could do that one using U substitution, right? Or I bet there's an integral table on the back. Do I have it? Yes, it's back there. There's an integral table somewhere for that one. Wait, what's sigma? Do we know what sigma is?
Q over the area.
What's the area in this case?
Pi r square.
Which r?
Big R.
Yep. So great. That's just some integral you could do. All right. Now, let's do this. What would be different if I put a washer on the test?
You would have limits on your integral.
Different limits. You'd go from radius inner to radius. Oh, I guess I should be careful here. I didn't put the limits on, right? I should do that really quick. The limits for this integral would go from 0, the smallest possible value of r, to capital R, the biggest possible value of little r. So if you had a washer, you might expect the lower limit to change. Anything else or not?
Your lambda or your
Your density.
yeah,
Yes.
density. There you go.
Yeah. So, right, that would change to some more complicated formula, but the procedure is still the same. Now, I have no idea if that made any sense to you or not, but I'm hoping that we put a lot of time into these types of problems earlier so that this is now a little bit easier. I don't know if that's going to be true. So, yeah, what's next? Let's see. I think we're gonna, let me just check one more thing here. I think we're pretty much done today. So I'm going to look at the schedule really quick. I'm going to go ahead and stop the live stream there.